Hello, my name is Tujayu.
Hello, my name is Faris.
Hello, my name is Tan Shui.
Hello, my name is Nurin.
Hi, my name is Shamimi.
Hello, my name is Dania.
And don't forget green! And we are going to present biodegradable
Cutleries.
The principle of green chemistry is basically a sustainable practice of chemical science where we ensure that whatever products or chemicals that we did is less polluting, it is safe, it reduces the waste, and most importantly, it uses a less hazardous synthesis and minimize the use of energy and material. The first principle is to prevent waste. PLA cutleries is not like those conventional method cutleries like polystyrene plastic, because polystyrene plastic is like a one-time use plastic. It's like when we already use it, we will throw. But PLA cutleries, we can recycle it back so that the polylactic acid can be extracted out, and then the polylactic acid is used back to make another PLA cutleries. So by this way, no wastage are made because it is better to not make any mess rather than cleaning it up.
The second principle of green chemistry is maximizing atom economy, which essentially means using as many atoms from the starting materials in the final product. In the case of polylactic acid production for biodegradable cutlery, this principle is realized through the use of renewable resources. Polylactic acid is derived from natural resources like cornstarch or sugarcane, where the carbon atoms from these feedstocks are efficiently incorporated into the polymer. This contrasts with the traditional plastics, where the starting materials might be petrochemicals, leading to a lower atom economy. By focusing on renewable resources, the production process minimizes waste and environmental impact, aligning with the green chemistry principle of maximizing atom economy. The third principle of green chemistry is less hazardous chemical synthesis, which is to employ methods that result in less hazardous chemical synthesis. In the case of polylactic acid, the production process involves a biologically based fermentation of sugars, followed by polymerization. This method significantly reduces the need for toxic chemicals compared to traditional plastic synthesis. Conventional plastics often require harsh chemicals and catalysts that can be harmful to both the environment and human health. Polylactic acid, on the other hand, utilizes a more gentler process with fewer hazardous byproducts. The fermentation process to reduce lactic acid can be carried out under mild conditions, avoiding the use of toxic reagents and minimizing environmental impacts.
Now I am going to continue this presentation about safer chemicals and products. And our journey begins with bio-based plasticizer derived from soybean oil, providing flexibility and softness to plastics, in stark contrast to their non-bio counterparts, often derived from fossil fuels. These natural alternatives offer a safer solution. Fossil fuel-derived plasticizers are known for their toxicity and potential harm to both wildlife and humans through endocrine disruption. Moving on to microbial inhibitors, we turn to nature's defense mechanism extracted from plants. Traditional plastic cutleries with non-natural microbial inhibitors possess environmental threats, contaminating water system, disrupting ecosystem, and contributing to antibiotic resistance among microorganisms. In contrast, plant-based inhibitors offer an eco-friendly alternative, combating microbial growth without adverse side effects. Now let's explore the mechanical and thermal aspects. Natural fibers from coconuts are incorporated into these sustainable plastics, enhancing both mechanical strength and thermal properties. This ensures that our products not only maintain biodegradability but also excel in performance. Next, safer solvents and reaction conditions. In the realm of PLA production, a beacon of safety shines bright. Lactic acid extraction, utilizing solvents like acetone, dimethyl sulfoxide (DMSO), and supercritical carbon dioxide (SCCO2), creates a secure environment. Operating under 200 degrees Celsius, this process ensures both efficiency and safety. In the conventional world of petroplastic, benzene takes center stage, but the spotlight turns ominous. Benzene dehydrogenation not only involves toxic elements but demand higher temperatures, putting both operators and the environment at risk. Picture this: PLA production, a symphony of eco-conscious methods, versus the petroplastic overture with this toxic solo. PLA use of lactic acid extraction creates a harmony of safety, utilizing solvents that treat lightly on the environment. Contrastingly, the petroplastic saga relies on benzene, a hazardous choice with a dangerous temperature dance. Next, I'll pass to my friend Chui.
Now, it's my turn. I'm going to talk about the principle of increased energy efficiency. This principle is mainly about design chemical processes and products that minimize the consumption energy throughout their life cycle. For this reason, we choose PLA as our ingredients. That's because the production of PLA generally requires less energy and lower temperature. And during this process, the carbon dioxide produced is offset by the carbon dioxide absorbed by the plants during photosynthesis. Now, let's take petroplastic as an example to show why PLA is better. To produce petroplastic, it requires high temperature and cracking and refining process. The electric power used during this process is derived from natural gas or coal that require high energy to extract them from environment. The next principle is use renewable resources. From these three words, it's easy to understand that the principle wants us to use renewable raw materials. In making PLA cutlery, the ingredient we use is often made from renewable resources such as cornstarch, potato starch, and other plant-based materials. These resources can be replenished through agriculture, and we can say that it is unlimited if we continue to cultivate it. On the other hand, petroplastic is made from fossil fuel-derived feedstock such as petroleum or natural gas. We know that this kind of feedstock is non-renewable and it might cause depletion of natural resources. And further, it might lead to habitat destruction or loss of biodiversity.
Hello everyone, I'm going to present about the 8 and 9 principle of green chemistry, which is avoid chemical derivatives and use catalysts. For avoid chemical derivatives, our PLA cutleries are made from PLA plastics. PLA plastic use biological fermentation methods. These methods often require fewer chemicals, contributing to a more sustainable and environmentally friendly process. PLA plastics use pure sources for lactic acid such as corn, sugarcane, and potatoes. This is essential in minimizing the need for extensive chemical purification process. Compared to PLA plastic, traditional petroplastics such as PET often rely on copious amount of reagent and extreme conditions to ensure the highest yield of desired products. This approach not only consumes a significant amount of resources but also lead to substantial waste and environmental impact. Moreover, the use of chemical synthesis methods in petroplastics production is another concern. While this method expedite the production process, they often come at the cost of environmental sustainability. Next is use of catalysts. For production of PLA plastic, we use magnesium acetate, which is a shining example of an environmentally friendly catalyst. Unlike conventional methods that use harsh reagent and extreme conditions, magnesium acetate promotes PLA polymerization efficiently. This aligns with green chemistry principle by reducing the environmental impact and enhancing the sustainability of polymer production. Moving on to enzymes such as lipase and protease, these biodegradable catalysts are a game changer in the world of green chemistry. Unlike conventional catalysts that can leave behind hazardous waste, enzyme can break down into harmless substance after use. Compared to PLA plastics, the production of petroplastic use catalysts such as Ziegler-Natta. Ziegler-Natta are incredibly effective but come with environmental concerns. They often rely on transition metals like titanium and vanadium, which can be scarce and may lead to the production of hazardous waste if not handled properly. Other than that, the production of petroplastic also use acid catalysts such as antimony. While effective in polymerization, antimony is a heavy metal with toxicity concern. It is used in conventional plastic manufacturing process, poses environmental risk, and can result in contamination, which is contradicting to the principle of green chemistry.
The 10th principle of green chemistry is design chemicals and products that degrade after use. PLA cutleries are made up of lactic acid, which is a natural compound, and they metabolize very easily in the environment. So as a result, they degrade into harmless products and leave a low impact on the environment. PLA goes through degradation through a few processes, such as enzymatic degradation, where microorganisms secrete specific enzymes such as PLA depolymerase and breaks down the PLA into lactic acid and lactide. Hydrolysis also breaks down PLA into lactic acid and lactide by reacting with water. Lactic acid and lactide can go through further reactions to produce carbon dioxide and water. On the other hand, conventional plastics are made up of petroleum-based plastics such as polypropylene and polystyrene, which takes hundreds of years to break down. This makes them non-biodegradable. The 11th principle of green chemistry is analyze in real time to prevent pollution. It is really important to design a reaction that can easily be monitored in real time, so chemists are able to make feedback and adjustments. Besides that, this also allows chemists to know when the reaction is done, so they can stop the reaction on time, and therefore reactants' time and energy will not be wasted. The metal Rit test is used to detect the production of lactic acid in glucose fermentation. The lactobacilli will produce a red color, which indicates that lactic acid has already been produced and no more reagents are needed further. The alternative method is the Voges-Proskauer test, but this method involves more steps and reagents, which may lead to more wastage in terms of reagents, energy, and time.
Last but not least, the 12th principle of green chemistry, which is minimizing potential for accidents. So in PLA cutleries and petroplastic cutleries, we look at this principle to ensure the safety for the handler, the environment, and the future generation. So for PLA cutleries, we use renewable feedstocks, which we can extract from a lower temperature and operating pH level. Compared to petroplastic cutleries, we need to operate at a higher risk of extraction processes of fossil fuels. This is significantly dangerous for the handlers. So if we are looking at the chemical side or at the atomic level, PLA or polylactic acid is not dangerous if it enters waterways. Compared to petroplastic cutleries, if the chemical enter the waterways, it would harm the water structure and the society surrounding it. So this is why PLA cutleries abide to 12 principles of green chemistry. Compared to petroplastic cutleries, PLA cutleries is a much more safer, environmental friendly, and sustainable option to choose from. So let's change to PLA cutlery.
Thank you. Bye-bye.